Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists at the very edge of our understanding, where the familiar boundaries of our solar system give way to the infinite expanse of interstellar space. You're settling in now, perhaps adjusting your pillow, finding that perfect position where your body can truly relax, and as you do, I want to share with you a story about a visitor. A silent traveler that has journeyed for millions, perhaps billions of years through the cosmic dark to arrive at our doorstep. This visitor has a name, though it's more of a designation really, Three-Eye Atlas. And while that might sound clinical, almost bureaucratic, what it represents is anything but ordinary. It's a question that might initially spark skepticism in your mind, and that's perfectly natural. But what if I told you that this object, this interstellar wanderer, might be carrying something with it? Not in the way a suitcase carries clothes or a ship carries cargo, but in a far more subtle, far more profound way that touches on some of the deepest mysteries of our universe. As we begin this journey together, let your mind drift to that place where scientific wonder meets philosophical contemplation, where the hard facts of astronomy blend seamlessly with the poetry of existence. Three Atlas is what we call an interstellar object, which means it didn't form in our solar system. It comes from somewhere else entirely, from around another star in another part of our galaxy, and it has been travelling through the vast emptiness between stars for an incomprehensibly long time. Think about that for a moment. While our Earth was still forming, while the dinosaurs roamed, while humanity took its first tentative steps, this object was already ancient, already on its journey through the cosmic void. And now, by pure chance, or perhaps by some cosmic design we don't yet understand, its path has brought it through our neighbourhood, close enough for us to detect, close enough for us to wonder. The discovery of Three-Eye Atlas wasn't accompanied by fanfare or dramatic announcements. It appeared quietly in our telescopes, a faint point of light moving against the background stars in a way that immediately told astronomers this was something special. You see, everything in our solar system moves in relatively predictable ways, bound by the sun's gravity in elegant elliptical dances that have been choreographed over billions of years. But Three-Eye Atlas moves differently. Its trajectory is hyperbolic, which in the gentle language of celestial mechanics means it's not bound to our sun at all. It's just passing through, like a cosmic tourist taking a brief detour through our stellar neighbourhood, before continuing on its endless journey. What makes this particularly fascinating, and what keeps me awake some nights with wonder, is that we've only recently developed the technology to even detect such objects. For all of human history, interstellar visitors like Three-Eye Atlas have been passing through our solar system unseen, unnoticed, carrying their secrets with them as they drift through the darkness. We're living in a unique moment, you and I, where for the first time our species can reach out with instruments sensitive enough to spot these faint travellers and ask profound questions about what they might mean. Consider this. If you compressed the entire history of our galaxy into a single day, humanity's ability to detect interstellar objects would occupy less than a fraction of a second at the very end. We've just opened our eyes to this phenomenon, and already we're discovering that these visitors might be more common than we ever imagined. Three-Eye Atlas is only the third confirmed interstellar object we've detected, following Oumuamua in 2017 and Borisov in 2019. But statisticians and astronomers suspect that countless others have passed through unnoticed, and many more are on their way. As you listen to my voice, as you let these ideas wash over you like gentle waves on a cosmic shore, I want you to imagine the scene when Three-Eye Atlas was first detected. Picture a quiet observatory, perhaps on a mountaintop where the air is thin and clear, where the stars shine with a brilliance that city dwellers rarely see. The telescope, a marvel of engineering and precision, slowly tracks across the sky, gathering ancient light that has travelled for years to reach us. The computers hum softly, processing vast amounts of data, looking for patterns, anomalies, anything that stands out from the cosmic background. And then, there it is, a point of light that shouldn't be there, moving in a way that nothing in our solar system should move. The astronomers who first noticed this anomaly probably didn't immediately realize what they had found. These discoveries often begin with confusion, with double-checking calculations, with quiet consultations between colleagues. "Have you seen this?" they might ask. "What do you make of this trajectory?" And slowly, as more observations are made, as the orbit is refined and calculated with ever greater precision, the realization dawns. This is something from beyond, a messenger from another star. Now, when I say messenger, I don't mean to imply intention or purpose in the human sense. 3i Atlas isn't carrying a plaque or a golden record like our Voyager spacecraft. But in a very real sense, it is carrying information. Every atom in its structure, every molecule of ice and grain of dust was formed in conditions utterly different from those in our solar system. The ratios of isotopes, the crystalline structure of its ice, the very chemistry of its being, all of these are encoded messages about its origin, about the star system where it formed, about the journey it has taken to reach us. This is where our contemplation tonight takes a particularly intriguing turn. What if 3i Atlas brings something with it? Not something designed or intended, but something fundamental, something that speaks to the interconnected nature of our galaxy. Scientists have long speculated about the possibility of material exchange between star systems. In the vast timescales of cosmic evolution, objects like 3i Atlas might serve as bridges, as carriers of material from one stellar system to another. And if that's true, if these interstellar wanderers really do facilitate a kind of slow, patient exchange of matter across the galaxy, then what might that mean for our understanding of our own origins? Let me paint you a picture of the cosmos that might help frame this question. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Each of these stars is on average separated from its nearest neighbors by distances so vast that light itself, the fastest thing in the universe, takes years to traverse them. If you could shrink the galaxy down so that our sun was the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. The entire galaxy, at this scale, would be about 100,000 miles across. In this vast ocean of space, stars are like islands, isolated and alone, each with their own planetary systems, their own chemistry, their own stories. But perhaps they're not as isolated as we thought. Perhaps objects like 3i Atlas are the threads that connect these islands, the slow boats that carry material from shore to shore across the cosmic ocean. It's a beautiful thought, isn't it? That even in the vast loneliness of space there might be connections, exchanges, a kind of slow conversation between the stars that has been going on for billions of years. As 3i Atlas approaches the inner solar system, something remarkable happens. The gentle warmth of our sun, barely perceptible at the vast distances where this object has spent most of its recent journey, begins to have an effect. If 3i Atlas is like other comets, and we have every reason to believe it shares at least some characteristics with them, then it contains volatile ices that have been frozen solid for eons. As these ices warm, they don't melt in the way ice melts on Earth. Instead, they sublime, transforming directly from solid to gas, creating a thin atmosphere around the object called a coma. This process is incredibly gentle, almost imperceptible. We're not talking about violent eruptions or dramatic transformations. Instead, imagine the slowest, most patient exhale you can conceive of, a breath that takes weeks or months to complete. As 3i Atlas breathes out its ancient ices, it creates a tail, a gossamer stream of gas and dust that flows away from the sun, pushed by the solar wind and radiation pressure. This tail, which can stretch for millions of miles, is made of material that formed around another star, in another time, under conditions we can only imagine. Think about what this means. Right now, as you lie there listening, our solar system is being gently dusted with material from another star. The atoms that make up this cosmic gift were forged in a stellar furnace light years away, assembled into molecules in the cold depths of an alien protoplanetary disk. frozen into the structure of 3I Atlas, and carried across the galaxy to be released here, now in our time. Some of these atoms might eventually find their way to Earth, becoming part of our atmosphere, our oceans, perhaps even part of life itself. This brings us to one of the most profound questions in science. How common is life in the universe, and how does it spread? For decades, scientists have debated the concept of panspermia, the idea that life might propagate through space, jumping from world to world like seeds carried on the cosmic wind. It's an ancient idea, really, one that speaks to our deep intuition that life is somehow fundamental to the universe, not just a lucky accident on one small planet. And while we have no evidence that 3I Atlas carries life, or even the precursors to life, its mere existence proves that material can and does travel between star systems. Let your mind wander with this possibility for a moment. If simple organic molecules, the building blocks of life as we know it, can survive the journey between stars locked in the ice of objects like 3I Atlas, then the galaxy might be far more interconnected than we ever imagined. Life might not arise independently on each suitable world, but might instead be part of a vast, slow, patient process of cosmic gardening, with objects like 3I Atlas serving as the gardeners, or perhaps more accurately, as the seeds blown by stellar winds from garden to garden. I want to be clear here that we're in the realm of speculation, of possibility rather than certainty. Science requires evidence, and we don't yet have evidence that 3I Atlas or any other interstellar object has ever carried life or its precursors between stars. But the beauty of science, the thing that makes it such a powerful tool for understanding our universe, is that it allows us to ask these questions, to consider these possibilities, and to design experiments and observations that might one day provide answers. As you drift deeper into relaxation, let's consider the journey that 3 Atlas has taken to reach us. We can't know exactly where it came from or how long it's been travelling, but we can make educated guesses based on its trajectory and what we know about the motion of stars in our galaxy. The most likely scenario is that 3I Atlas was ejected from its home system millions or even billions of years ago, perhaps during the chaotic early days of planet formation, when gravitational interactions between growing planets could fling smaller objects out into interstellar space. Picture, if you will, a young star system, not unlike our own solar system 4.5 billion years ago. The star has recently formed from a collapsing cloud of gas and dust, and around it, a disk of material is slowly condensing into planets. It's a violent nursery, with collisions and near misses happening constantly as planetesimals, the building blocks of planets, grow through accretion. In this chaos, some objects gain enough velocity to escape the star's gravity entirely. They become interstellar wanderers, cosmic orphans destined to drift through the galaxy until, by pure chance, they encounter another star. For 3 Atlas, that star is our Sun. After eons of solitary travel through the near-perfect vacuum of interstellar space, where the average density is about 1 atom per cubic centimetre, emptier than any vacuum we can create on Earth, it has entered a relatively crowded neighbourhood. Our solar system, with its 8 planets, dozens of moons, and countless asteroids and comets, must seem positively bustling compared to the emptiness 3I Atlas has known. The approach of 3I Atlas to our solar system would have been gradual, almost imperceptible at first. For thousands of years, it would have been falling toward our Sun, accelerating slowly under the influence of our star's gravity. But because of its tremendous initial velocity, the speed it carried from its original ejection, it will never be captured. Instead, it will swing around the Sun in a hyperbolic arc, using our star's gravity as a slingshot to change its direction before heading back out into interstellar space, never to return. This brief encounter, lasting perhaps a year or two from our perspective, is the only chance we'll ever have to study this particular object. Once it leaves, it will be gone forever, continuing its journey through the galaxy, perhaps to visit other star systems millions of years in the future. There's something both sad and beautiful about this transience, this cosmic passing in the night. We're witnessing a moment that will never repeat, a unique event in the history of our solar system. As we move deeper into our contemplation, into the second phase of our journey tonight, let's explore how we actually detected 3i Atlas, how we plucked this faint whisper from the cosmic noise. The story of its discovery is not one of dramatic revelation, but of patient observation, of careful analysis, of technology and human curiosity working in harmony to reveal something extraordinary hiding in plain sight. Modern astronomy is as much about data processing as it is about pointing telescopes at the sky. Every night, automated survey telescopes scan vast swathes of the heavens, taking thousands of images, each one containing millions of stars, galaxies, and other celestial objects. These images are compared to previous observations, looking for anything that has changed, anything that has moved, anything that doesn't belong. It's like looking for a single grain of sand on a beach that wasn't there yesterday, except the beach is the entire sky, and the grain of sand is moving. The Asteroid-Terrestrial Impact Last Alert System, or ATLAS, is one of these automated sentinels. Developed by the University of Hawaii, ATLAS consists of telescopes that scan the entire visible sky multiple times each night, looking primarily for asteroids that might pose a threat to Earth. But in the process of looking for potential hazards, ATLAS also discovers comets, variable stars, supernovae in distant galaxies, and occasionally something truly special like an interstellar visitor. When 3i Atlas first appeared in the data, it would have been just another moving point of light among thousands. The initial detection algorithms wouldn't have recognized it as anything particularly special. It was only when astronomers calculated its orbit, when they traced its path backward and forward in time, that they realized this object wasn't bound to our sun. The mathematics told a story of an object that had been traveling through interstellar space for longer than our species has existed, longer than complex life has existed on Earth, possibly longer than our planet itself has existed. Imagine being the astronomer who first realized what they were looking at. You're sitting at your computer, perhaps sipping coffee, going through the routine process of checking orbital calculations, when suddenly the numbers don't make sense. You check again, run the calculations once more, and slowly it dawns on you. This object came from outside our solar system. You're looking at something that formed around another star, something that has traveled across the galaxy to visit us. In that moment, you're the first human being to know that we have another interstellar visitor. The process of confirming such a discovery is methodical and careful. Other observatories are alerted, additional observations are made, and the orbit is refined with ever greater precision. Each new data point adds confidence to the conclusion. Yes, this is really an interstellar object. The international astronomical community springs into action, with telescopes around the world and in space turning to observe 3i Atlas, each one contributing pieces to the puzzle of understanding this cosmic visitor. What's particularly fascinating about the detection of 3i Atlas is how it reveals the ghost-like nature of our observation of the cosmos. We're not seeing 3i Atlas as it is right now, we're seeing it as it was when the light left it, which, depending on its distance, could be minutes or hours ago. And the light we're seeing isn't even coming directly from 3i Atlas itself. It's sunlight, reflected off its surface, carrying information about its composition, its size, its rotation. Encoded in the subtle variations of brightness and colour, this reflected light is incredibly faint. 3i Atlas is likely only a few miles across, a tiny speck in the vastness of space, visible only because our telescopes and detectors have become so incredibly sensitive. We're essentially looking at a small dark mountain floating in space, hundreds of millions of miles away, illuminated only by the distant sun. That we can detect such an object at all, let alone study it in detail, is a testament to how far our technology has come. As astronomers studied the light from 3i Atlas more carefully, they began to notice patterns. The brightness varies slightly over time, suggesting that the object is rotating, showing different faces to us as it tumbles through space. The color of the light tells us about its surface composition, whether it's rocky, icy, or covered in organic compounds. The way the brightness changes as 3i Atlas moves closer to the Sun tells us about its structure, about how it responds to heating, about what volatile materials it might contain. Each of these observations is like a piece of a cosmic puzzle, and astronomers around the world are working to put these pieces together to understand what 3i Atlas really is. Is it more like a comet, with lots of ice that will sublime as it approaches the Sun? Is it more like an asteroid, a chunk of rock and metal with little volatile content? Or is it something else entirely, something we haven't seen before, something that will challenge our understanding of how planetary systems form and evolve? The spectroscopic analysis of 3i Atlas has been particularly revealing. By spreading its light out into a spectrum, like a prism spreading sunlight into a rainbow, astronomers can identify the chemical fingerprints of different elements and compounds. Each atom and molecule absorbs and emits light at specific wavelengths, creating a unique pattern that serves as its signature. By reading these signatures in the light from 3i Atlas, we can determine what it's made of, even though we can't physically touch it or bring a sample back to Earth. What we've found so far suggests that 3i Atlas has a composition not entirely unlike comets from our own solar system, but with intriguing differences. The ratios of certain isotopes, the presence or absence of specific compounds, the overall chemistry, all of these show subtle variations from what we're familiar with. These differences are like an accent in a language, telling us that while 3i Atlas speaks the same basic chemical language as objects in our solar system, it learned that language in a different place, under different conditions. The detection of 3i Atlas also raises profound questions about how many such objects might be passing through our solar system undetected. If we found 3 interstellar objects in just a few years of looking with modern technology, how many have we missed? How many are out there right now, too faint for our current telescopes to see? Statistical models suggest that at any given time, there might be thousands of interstellar objects within the orbit of Neptune, silent visitors from other stars that we simply can't detect yet. This hidden population of interstellar wanderers represents a vast untapped reservoir of information about other star systems. Each one is a time capsule, preserving information about its place of origin, about the conditions under which it formed, about the chemical and physical processes that shaped it. If we could study enough of them, we could begin to build a picture of how planetary systems throughout our galaxy form and evolve, how common or rare our own solar system might be, and perhaps even whether the conditions for life exist elsewhere. As you continue to relax, to let these ideas flow through your mind like a gentle stream, consider the technology that makes these discoveries possible. The telescopes that detected 3i Atlas are marvels of engineering, with mirrors polished to near-atomic smoothness, detectors sensitive enough to count individual photons, and computer systems capable of processing terabytes of data every night. But beyond the hardware, there's something even more remarkable: the human curiosity and ingenuity that drives us to build these instruments, to look up at the night sky and ask, what's out there? The Atlas system that discovered 3i Atlas was originally designed to protect Earth from asteroid impacts, to serve as an early warning system for cosmic hazards. But like many scientific instruments, it has revealed far more than its designers initially intended. In looking for dangers, we've found wonders. In trying to protect our world, we've discovered that we're part of a much larger cosmic community, connected to other star systems by these traveling ambassadors of ice and rock. The data from Atlas flows continuously, night after night, a river of information about the cosmos. Most of it is routine, known asteroids following their predictable paths, familiar stars varying in brightness according to well-understood patterns. But occasionally, hidden in this flow of data, There's something special, something that doesn't fit the patterns, something that tells us the universe still has surprises in store for us. The computer algorithms that first flag potential interstellar objects are themselves fascinating. They're trained on millions of observations of known solar system objects, learning to recognize the subtle differences in motion that distinguish a bound object from an unbound one. It's a kind of artificial intelligence, though not in the science fiction sense. More like a very sophisticated pattern recognition system that can spot anomalies in vast data sets that would take human astronomers years to examine manually. But ultimately, it still takes human judgment to confirm these discoveries. The algorithms can flag potential candidates, but it's human astronomers who must verify the observations, calculate the orbits with precision, and make the call. Is this really an interstellar visitor, or is there some other explanation? This partnership between human intuition and machine processing power is what makes modern astronomy so powerful, allowing us to discover things that would have been impossible to find just a generation ago. As we transition into contemplating the long journey that brought 3i Atlas to us, let your mind expand to encompass the vast scales of time and space involved. The journey of 3i Atlas isn't just a trip through space, it's a voyage through time, a passage through eras so vast that they dwarf all of human history, all of Earth's history, even the history of our solar system itself. To understand the journey of 3i Atlas, we need to think about the structure of our galaxy and how objects move within it. The Milky Way is not a static structure but a dynamic rotating system where stars orbit around the galactic center, taking hundreds of millions of years to complete a single circuit. Our Sun, with its retinue of planets, is currently about 26,000 light-years from the galactic center, orbiting at a speed of about 514,000 miles per hour. Even at this tremendous velocity, it takes our solar system about 230 million years to complete one orbit around the galaxy, a period sometimes called a cosmic year. During the time 3i Atlas has been traveling, our solar system has likely completed several orbits around the galaxy. The stars we see in our night sky have all moved to different positions. Constellations have changed shape. Some stars have been born, lived their entire lives, and died, exploding as supernovae or fading as white dwarfs. The galaxy itself has evolved, with spiral arms winding tighter or looser, star-forming regions flaring to life and then fading to darkness. 3i Atlas has witnessed, in its blind, unconscious way, changes in the galaxy that no human eyes will ever see. It has passed through regions of space with different densities, different temperatures, different magnetic fields. It may have travelled through the shock waves from supernovae, through stellar nurseries where new stars are being born, through the vast voids between spiral arms where the darkness is nearly absolute. Each of these passages would have left subtle marks on 3i Atlas, tiny changes in its surface chemistry, microscopic impacts from interstellar dust grains, a slow weathering by cosmic rays and radiation. The interstellar medium through which 3i Atlas has travelled is not empty, though it's closer to a perfect vacuum than anything we can create on Earth. On average, interstellar space contains about 1 atom per cubic centimetre, compared to about 10^19 atoms per cubic centimetre in Earth's atmosphere at sea level. But even this incredibly thin medium has an effect over the vast distances and times involved in interstellar travel. 3i Atlas has been gently sandblasted by individual atoms and molecules, mostly hydrogen and helium, for millions of years. This process, called cosmic ray spallation, slowly changes the surface chemistry of the object, creating isotopes that can only form through these high-energy collisions. The temperature that 3i Atlas experienced during its interstellar journey would have been incredibly cold, just a few degrees above absolute zero. In the darkness between stars, with no nearby source of heat, objects cool to the temperature of the cosmic microwave background radiation, about 2.7 Kelvin or 454 degrees Fahrenheit. At these temperatures, Even gases like nitrogen and oxygen would be frozen solid. Any volatile compounds in 3I Atlas would have been locked in a deep freeze for eons, preserved in their original state from when the object first formed. But the cold of interstellar space is not uniform. As 3I Atlas drifted through the galaxy, it would have occasionally passed closer to stars, perhaps coming within a few light years of them. During these passages, the starlight would have warmed it slightly, perhaps causing some subtle changes in its surface, some minor sublimation of the most volatile ices. These brief warming episodes would have been like momentary thaws in an eternal winter, lasting perhaps a few thousand years before 3I Atlas drifted back into the cold darkness. The radiation environment of interstellar space would have also affected 3I Atlas throughout its journey. Cosmic rays, which are high-energy particles accelerated by supernovae and other violent cosmic events, would have continuously bombarded its surface. These particles can penetrate deep into solid material, causing nuclear reactions that transmute one element into another, creating radioactive isotopes that slowly decay over time. By studying these isotopes, if we could somehow get a sample of 3I Atlas, we could potentially determine how long it has been travelling through interstellar space. The journey of 3I Atlas also speaks to the incredible stability of orbits in the emptiness between stars. Without any significant gravitational perturbations, an object in interstellar space will continue on essentially the same trajectory for billions of years. It's the ultimate expression of Newton's first law of motion. An object in motion stays in motion unless acted upon by an external force. In the vast emptiness between stars, there are essentially no external forces, allowing 3I Atlas to maintain its course across the galaxy with a precision that no human-made navigation system could match. Consider the loneliness of this journey. For potentially billions of years, 3I Atlas has been alone in the darkness, with no companion objects, no neighbouring worlds, nothing but the distant stars as silent witnesses to its passage. If we could somehow experience time from the perspective of 3I Atlas, we would witness the slow dance of the stars, their proper motions causing them to drift across the sky over millions of years. We would see stellar nurseries flare to life in brilliant displays of star formation, then fade as the young stars dispersed. We would witness the galaxy itself rotating, its spiral arms winding and unwinding in a cosmic dance that takes hundreds of millions of years to complete. But 3I Atlas experiences none of this. It has no consciousness, no awareness, no way to mark the passage of time. It simply exists, a collection of atoms bound together by chemical and physical forces, following the laws of physics with perfect fidelity. And yet, in its structure, in its composition, in the subtle details of its chemistry and mineralogy, it carries information about its origin, about the star system where it formed, about the conditions that existed there billions of years ago. It's a message in a bottle, cast into the cosmic ocean by forces beyond its control, carrying information across the galaxy without intention or purpose, but carrying it nonetheless. The approach of 3I Atlas to our solar system would have begun long before we detected it, long before our species even existed. As it fell toward our sun from interstellar space, it would have been accelerating gradually, imperceptibly, its velocity increasing by just a few meters per second each year. This slow acceleration continued for thousands, perhaps millions of years. As 3 Atlas responded to the sun's gravity from distances so vast that our star would have appeared as nothing more than a slightly brighter point of light among millions of others, the boundary of our solar system is not a sharp line but a gradual transition. The heliopause, where the solar wind meets the interstellar medium, is about 11 billion miles from the sun, but the sun's gravitational influence extends much farther, out to the Oort cloud, a spherical shell of icy objects that may extend nearly a light-year from our star. 3 Atlas would have passed through these outer regions years or decades before we detected it, a silent intruder in the cold darkness at the edge of our solar system. As 3I Atlas crossed through the Oort cloud, it might have passed within a few million miles of some of the trillions of comets thought to reside there. These near misses, too distant to significantly affect its trajectory, represent missed opportunities for cosmic collisions that could have created spectacular displays. But space is vast and empty, and the chances of 3I Atlas actually hitting anything during its passage through our solar system are essentially zero. It will complete its journey as it began it, alone and untouched, a cosmic wanderer passing through without leaving a physical trace. The inner solar system, where Earth resides, must seem positively crowded to an object that has spent eons in the emptiness of interstellar space. Here, the sun's warmth is palpable, its radiation pressure measurable, its magnetic field detectable. The planets exert their own gravitational influences, creating a complex dance of forces that slightly modify the trajectory of passing objects. For 3I Atlas, these perturbations are minor, insufficient to capture it or significantly alter its path, but they're enough to leave their mark on its orbit, allowing us to detect the gravitational signatures of our solar system's major planets in its motion. As 3I Atlas warms in the increasing sunlight, chemical and physical processes that have been dormant for perhaps billions of years begin to stir. If it contains water ice, that ice begins to sublime at temperatures above about 150 Kelvin, still far colder than anything we experience on Earth. Carbon dioxide ice sublimes at even lower temperatures, around 80 Kelvin. These phase transitions from solid directly to gas create the coma and tail that make comets such spectacular objects in our sky. Though for 3I Atlas, being an interstellar visitor, this display might be more subtle, more alien than what we're used to seeing from our local comets. The sublimation process is gentle, but profound. Molecules that have been locked in place since 3I Atlas formed are suddenly free to escape into space. Each molecule that leaves carries with it a tiny bit of momentum, and the cumulative effect of trillions of molecules escaping can actually change the object's trajectory slightly, a phenomenon known as non-gravitational acceleration. This effect, first observed in detail with Oumuamua, adds another layer of mystery to these interstellar visitors. The forces involved are tiny, but over time they can accumulate to produce measurable changes in an object's path. As we observe 3I Atlas during its passage through our solar system, we're seeing it in a state of transformation. The cold, dormant object that entered our solar system is being awakened by the sun's warmth, revealing aspects of its nature that have been hidden for eons. It's like watching a flower bloom in extreme slow motion. A gradual unveiling of characteristics that tell us about both its current state and its deep history. The dust and gas released by 3I Atlas as it warms don't simply disappear. They become part of our solar system, at least temporarily. The gas molecules will eventually be swept out of the solar system by the solar wind, but some of the dust particles might remain, joining the zodiacal cloud of dust that fills the inner solar system. In this way, 3I Atlas leaves a subtle mark on our cosmic neighborhood, contributing material from another star system to the mix of particles that occasionally create meteor showers when Earth passes through them. Some of these dust particles might eventually find their way to Earth. They would enter our atmosphere as microscopic meteors, too small to create visible shooting stars but detectable by specialized instruments. When these particles settle to Earth's surface, they become part of our planet, alien atoms incorporated into our world's geology. It's a humbling thought that right now, today, Earth might be receiving material that formed around another star billions of years ago, delivered by couriers like 3I Atlas. The study of 3I Atlas during its brief passage through our solar system is a race against time. Every day it moves farther from the sun, growing fainter and more difficult to observe. Eventually it will fade beyond the detection limits of even our most powerful telescopes, returning to the darkness from which it came. We have perhaps a year or two to learn everything we can about this visitor before it's gone forever, continuing its journey through the galaxy, perhaps to visit other star systems millions of years in the future. This temporal pressure adds urgency to our observations, but also poignancy. We're witnessing a unique event, a cosmic encounter that will never repeat. The next interstellar object we detect will be different, with its own history, its own composition, its own mysteries. Each one is a unique sample from another part of the galaxy, a piece of a vast puzzle that we're only beginning to assemble, and with each observation, each measurement, each spectrum we collect, we're adding to our understanding not just of these individual objects, but of the galaxy as a whole, of the processes that shape planetary systems, of our own place in the cosmic order. As you continue to drift deeper into relaxation, feeling the weight of your body settling into complete comfort, let's turn our attention to the very substance of 3i Atlas, to the ice and rock and perhaps organic compounds that make up its physical form. What secrets might be locked within those frozen layers, waiting to be revealed by the gentle warmth of our sun? What stories could those molecules tell if we could read their chemical language with perfect fluency? The ice that forms the bulk of 3i Atlas is not like the ice in your freezer, or even the ice at Earth's poles. This is ice that has been cold for so long, compressed by its own weight for so many eons, that it has taken on properties we rarely see on Earth. In the deep cold of interstellar space, water ice can exist in forms that are alien to our everyday experience. Amorphous ice that lacks crystalline structure. Cubic ice with different molecular arrangements. Ice that has been transformed by billions of years of cosmic ray bombardment into something that carries the scars of its incredible journey. When we think about ice, we usually picture the familiar hexagonal crystals that create the beautiful patterns of snowflakes. But in the extreme conditions where 3i Atlas formed, and through which it has travelled, ice can take on at least 17 different crystalline forms, each stable only under specific conditions of temperature and pressure. Some of these exotic ices are denser than liquid water, some conduct electricity, some have magnetic properties. The particular forms of ice present in 3i Atlas could tell us about the conditions in its parent star system, about the temperatures and pressures present when it formed, about the journey it has taken to reach us. Mixed within this ice are likely other frozen gases: methane, ammonia, carbon dioxide, carbon monoxide, nitrogen, each with its own story to tell. The ratios of these different ices, what planetary scientists call the ice inventory, varies from star system to star system depending on the temperature and chemical composition of the protoplanetary disk where they formed. In our solar system, we see different ice compositions at different distances from the Sun, a pattern that reflects the temperature gradient in our early solar nebula. The ice inventory of 3i Atlas could reveal similar information about its home system, giving us a window into the conditions around another star billions of years ago. But perhaps most intriguing are the organic compounds that might be present in 3i Atlas. When we say organic in this context, we don't necessarily mean biological. We mean carbon-based molecules that form the complex chemistry from which life as we know it emerges. Radio observations of interstellar clouds have revealed a rich chemistry of organic molecules floating in space: methanol, formaldehyde, amino acids, even sugars. These molecules can become incorporated into comets and asteroids as they form, locked away in ice for billions of years like insects preserved in amber. The idea that 3i Atlas might carry organic molecules from another star system is not just speculation. We know from studying meteorites that fall to Earth that some contain complex organic compounds, including amino acids that are the building blocks of proteins. We've detected organic molecules in the comas of comets from our own solar system, and laboratory experiments have shown that when ice containing simple molecules like water, methane, and ammonia is exposed to radiation, the kind of radiation that 3i Atlas has been bathed in for eons, complex organic molecules form spontaneously. Imagine the journey these molecules have taken. Formed perhaps in the cold outer reaches of an alien planetary system, incorporated into the growing body of 3i Atlas as it accreted from dust and ice, then carried across the galaxy for billions of years, During this time, cosmic rays would have been constantly modifying them, breaking some apart, causing others to combine in new ways, creating a complex chemistry that evolved slowly over cosmic time. The organic inventory of 3i Atlas is not just a snapshot of conditions in its home system, but a record of its entire journey, written in molecular form. The surface of 3i Atlas tells its own story. After billions of years of exposure to the interstellar medium, the outer few meters would be heavily processed, what scientists call space-weathered. Cosmic rays would have created a rind of modified material, darker and redder than the pristine ice below. This process, known as irradiation reddening, creates complex carbon chains called tholins that give many outer solar system objects their characteristic reddish-brown color. The depth of this weathered layer, its exact composition, the degree of processing, all of these details encode information about how long 3i Atlas has been traveling and what environments it has passed through. Beneath this weathered rind, if we could somehow drill down into 3i Atlas, we would find layers like the pages of a book, each one recording a different chapter in its history. The deepest, most protected ice would be the most pristine, preserving the original conditions from when 3i Atlas formed. Moving outward, we would see the effects of various processing events, perhaps a layer that was partially melted during a close approach to its parent star, another that shows evidence of collision with another object, another that was modified during a passage through a particularly dense region of the interstellar medium. These layers wouldn't be uniform or perfectly horizontal like sedimentary rocks on Earth. The slow tumbling of 3i Atlas through space, its rotation that we can observe as periodic changes in brightness, means that different parts of its surface have been exposed to different conditions over time. One hemisphere might show more space weathering than another. One region might have been shielded from cosmic rays while another was fully exposed. This three-dimensional complexity makes 3i Atlas not just a message from another star, but a puzzle, a coded record that we're only beginning to learn how to read. The minerals embedded within the ice of 3i Atlas are equally fascinating. These tiny grains of rock and metal, some no larger than smoke particles, formed in conditions very different from those in our solar system. Some might be pre-solar grains, particles that actually predate the formation of 3i Atlas's parent star, inherited from the interstellar medium and preserved for billions of years. These grains are like cosmic fossils, preserving information about stellar processes that occurred before 3i Atlas's home system even existed. The isotopic composition of these minerals provides another layer of information. Isotopes are variants of elements that have different numbers of neutrons, and their ratios can tell us about the nuclear processes that created them. For example, the ratio of oxygen-16 to oxygen-18 varies depending on the temperature at which water ice formed. The presence of certain radioactive isotopes and their decay products can tell us about the age of the material and the types of stellar processes that contributed to its formation. Each isotopic ratio is like a fingerprint, unique to the conditions under which the material formed. Some of the most interesting minerals that might be present in 3i Atlas are those that could only form in the presence of liquid water. On Earth, we find such minerals in meteorites, evidence that their parent bodies once contained liquid water, heated by radioactive decay or impacts. If similar minerals exist in 3i Atlas, they would tell us that at some point in its history, perhaps in its very early days, parts of it were warm enough for water to exist in liquid form. This would have profound implications for the possibility of prebiotic chemistry occurring within 3i Atlas itself. The very structure of 3i Atlas, whether it's a solid chunk of rock and ice or a loose aggregation of smaller particles held together by weak forces, tells us about its formation and history. If it's a rubble pile, as some scientists suspect many comets are, then it's essentially a flying collection of pristine samples from its parent system, each particle potentially preserving different information about conditions during formation. If it's a solid, monolithic object, then it might have undergone more processing, more heating and compression, which would tell a different story about its origins. As 3I Atlas approaches the Sun and begins to warm, these various components respond differently. Water ice sublimes at one temperature, carbon dioxide at another, more exotic ices at still others. This differential sublimation creates a complex sequence of activity as 3I Atlas warms, like a chemical clock that reveals different components at different times. By observing which gases appear in the coma at which distances from the Sun, we can infer the composition of the ice, even though we can't directly sample it. The dust particles released along with the gas are equally informative. Their size distribution, their composition, their optical properties all provide clues about the conditions under which they formed. Some might be fluffy aggregates that preserve their structure from the early days of 3I Atlas's parent system. Others might be compact grains that have been processed and modified over billions of years. Each particle is a tiny world unto itself, with its own history, its own story to tell about the cosmic journey of 3I Atlas. The possibility that 3I Atlas might carry water is particularly intriguing. Water is, as far as we know, essential for life as we understand it, and its distribution throughout the galaxy is a key factor in assessing the potential habitability of other worlds. If interstellar objects like 3I Atlas regularly deliver water to planetary systems, they could play a crucial role in making planets habitable. Earth's water might have been delivered, at least in part, by comets and asteroids from our own solar system. Could some of it have come from interstellar visitors like 3I Atlas? The chemical signatures in Earth's water, particularly the ratio of heavy water containing deuterium to regular water, suggest multiple sources for our planet's oceans. Some water appears to have come from the inner solar system, some from comets formed in the outer solar system, and perhaps some from even farther away. Every interstellar object that passes through our solar system and releases water vapor adds its own isotopic signature to the mix, its own contribution to the cosmic reservoir from which planets can draw. Beyond water, 3 Atlas might carry other volatiles that are important for planetary atmospheres and potentially for life. Nitrogen, which makes up most of Earth's atmosphere, carbon dioxide, which is crucial for climate regulation and photosynthesis, methane, which can be both a biosignature and a greenhouse gas. All of these might be present in the ice of 3I Atlas. The delivery of these volatiles by interstellar objects could help explain why planetary atmospheres throughout the galaxy might share certain similarities, despite forming around different stars under different conditions. The organic molecules potentially present in 3I Atlas are perhaps the most tantalizing component of all. Laboratory experiments have shown that when ice containing simple organic molecules is subjected to radiation, more complex molecules form, including amino acids, the building blocks of proteins. Some scientists have even detected sugars and other prebiotic molecules in meteorites. If 3I Atlas carries such molecules from another star system, it raises profound questions about the universality of organic chemistry and the potential for life throughout the galaxy. These organic molecules wouldn't need to be biological in origin to be significant. The mere fact that complex organic chemistry can occur in the cold, irradiated environment of interstellar space suggests that the building blocks of life might be common throughout the galaxy. Every star system might be seeded with these molecules, either formed locally or delivered by interstellar wanderers like 3I Atlas. This cosmic seeding could mean that whenever conditions are right, liquid water, appropriate temperatures, energy sources, life has the raw materials it needs to emerge. The idea that 3I Atlas might be carrying microscopic passengers, actual microorganisms that could survive the journey between stars, is more speculative but not entirely impossible. We know that certain extremophiles on Earth can survive in conditions that seem impossibly harsh, in the vacuum of space, in intense radiation, in extreme cold. Experiments on the International Space Station have shown that some bacteria and even small animals called tardigrades can survive exposure to space for extended periods. If life exists elsewhere in the galaxy, and if it's as resilient as some Earth organisms, could it hitch a ride on objects like 3I Atlas? This possibility, known as lithopanspermia, has been debated by scientists for over a century. The idea is that life could spread through the galaxy not by deliberate space travel, but by natural processes, riding on rocks and ice ejected from one planetary system and eventually falling into another. It's a beautiful concept. Life is a kind of cosmic infection, spreading slowly but inevitably throughout the galaxy, each habitable world eventually becoming inhabited through this patient natural process. Even if 3i Atlas doesn't carry actual living organisms, it might carry the chemical templates that could jumpstart life on a sterile world. Complex organic molecules, delivered to a young planet with the right conditions, could undergo further chemical evolution, eventually leading to self-replicating systems and ultimately to life. In this scenario, interstellar objects like 3i Atlas are like cosmic seeds, carrying not life itself, but the potential for life. The chemical instructions that, given the right conditions, could bloom into biology. As you lie there, feeling yourself sinking deeper into relaxation with each breath, consider the trail that 3i Atlas is leaving through our solar system right now. It's not just passing through, it's actively shedding material, leaving a stream of gas and dust in its wake like a cosmic contrail. This trail, invisible to the naked eye but detectable by our instruments, is made of atoms and molecules that formed around another star that have travelled across the galaxy and that are now becoming part of our solar system, at least temporarily. The tail of 3i Atlas, if it develops one as it approaches the Sun, is a remarkable phenomenon. Driven by the solar wind and radiation pressure, the tail always points away from the Sun, regardless of the direction 3 Atlas is actually moving. It's like a cosmic weather vane, showing the direction of the solar wind, but made of material from another star system. The tail can stretch for millions of miles, a gossamer thread connecting 3i Atlas to the space through which it's passing, a visible sign of the material exchange between this interstellar visitor and our solar system. The composition of this tail tells us about the interior of 3i Atlas. As different ices sublime at different temperatures, the composition of the tail changes as 3i Atlas approaches and then recedes from the Sun. First might come the most volatile compounds, those that turn to gas at the lowest temperatures. Then, as 3i Atlas warms further, water ice begins to sublime, potentially creating a dramatic increase in activity. The dust released along with the gas reveals the non-volatile component, the rocky and metallic particles that were embedded in the ice. Some of this dust will follow 3i Atlas back out into interstellar space, but some will remain in our solar system, at least for a while. These particles will orbit the Sun on their own trajectories, gradually spreading out to form a very thin, very diffuse cloud. Eventually most will be swept out of the solar system by the solar wind, or will spiral into the Sun, but for years or decades they'll be part of our cosmic neighbourhood, alien dust mixed with the native dust of our solar system. The gas released by 3i Atlas has a different fate. These molecules, once they escape the weak gravity of 3i Atlas, are picked up by the solar wind and carried outward at hundreds of kilometers per second. They'll reach the outer planets in a matter of weeks or months, and eventually they'll cross the heliopause and return to interstellar space. But they won't return unchanged. They'll carry with them information about our solar system. They'll be ionized by our Sun's radiation. They'll have interacted with our solar magnetic field. They'll have been part of our heliosphere, however briefly. This exchange of material between 3 Atlas and our solar system is happening right now, as you listen to these words. Atoms that have been locked in ice for billions of years are being released, becoming part of the solar wind, interacting with the planets and moons of our solar system. Some might eventually find their way to Earth, raining down as microscopic meteors, becoming part of our atmosphere, our oceans, perhaps even being incorporated into living organisms. It's a profound thought that your body might someday contain atoms that arrived on 3i Atlas from another star. The dust particles released by 3i Atlas are particularly interesting because they could potentially be collected and studied directly. Several spacecraft have collectors designed to capture interplanetary dust particles and if any of these happened to encounter dust from Thruar or Atlas, we would have actual samples of material from another star system. These samples would be incredibly valuable, allowing us to perform detailed laboratory analyses that are impossible with remote observations. We could measure isotope ratios with extreme precision, look for pre-solar grains, search for organic molecules, perhaps even look for signs of past liquid water or other processing. The distribution of dust along 3I Atlas's orbit creates what astronomers call a meteoroid stream. If Earth happens to pass through this stream in the future, we might see meteors that originated from another star system, an interstellar meteor shower. These meteors would be distinguishable from ordinary meteors by their high velocity and their trajectory, coming from a direction that doesn't correspond to any known source in our solar system. Imagine looking up at the night sky and seeing a shooting star that began its journey around another sun billions of years ago. The interaction between the solar wind and the material released by 3I Atlas creates complex electromagnetic phenomena. The gas becomes ionized, creating a plasma that interacts with the solar magnetic field. This interaction can create waves and instabilities that propagate through the solar wind, potentially affecting spacecraft and even generating radio emissions that we can detect from Earth. It's as if 3I Atlas is playing a cosmic instrument, creating electromagnetic music as it passes through our solar system. The rate at which 3I Atlas loses mass tells us about its structure and composition. A loosely bound rubble pile would lose mass more easily than a solid, monolithic object. An object rich in volatile ices would be more active than one composed mainly of rock. By carefully measuring the mass loss rate and how it changes with distance from the Sun, we can infer the internal structure of 3I Atlas. Even though we can't see inside it directly, it's like deducing the internal structure of a building by watching how it responds to changes in temperature and wind. The particles released by 3I Atlas don't all behave the same way. The smallest particles, those less than a micrometer across, are strongly affected by radiation pressure and are blown out of the solar system almost immediately. Larger particles, those big enough to feel gravity more than radiation pressure, follow more complex trajectories. Some might go into orbit around the Sun, some might impact planets or moons, some might be captured by planetary gravity and become temporary satellites. Each particle has its own story, its own fate in our solar system. The chemical reactions occurring in the coma of 3I Atlas as it warms are a natural laboratory for astrochemistry. As different molecules are released from the ice and exposed to solar radiation, they break apart and recombine in new ways. Photodissociation breaks complex molecules into simpler ones, while other reactions create new compounds that weren't present in the original ice. By studying the chemistry of the coma, we can learn about chemical processes that are important throughout the universe, from star-forming regions to planetary atmospheres. Some of the most interesting chemistry might be happening at the interface between the ice and the vacuum of space. Here, in a region just a few molecules thick, conditions are unlike anything we can easily recreate in laboratories on Earth. The combination of ultra-high vacuum, intense radiation, and slowly subliming ice creates a unique environment where unusual chemical reactions can occur. Some scientists think this interface region might be where complex organic molecules form, perhaps even where the precursors to life could emerge. The possibility that 3I Atlas might be actively producing organic molecules as it passes through our solar system is fascinating. The combination of simple molecules from the ice, energy from solar radiation, and the unique conditions in the coma could be driving organic synthesis right now, creating new molecules that have never existed before. These newly formed organics would join the stream of material flowing away from 3I Atlas, potentially seeding our solar system with fresh organic compounds. As we contemplate the material exchange between 3I Atlas and our solar system, we're really thinking about the interconnectedness of the galaxy. Every star system loses material to interstellar space through various processes: stellar winds, planetary impacts that eject debris, the gradual escape of atmospheric gases from planets, and every star system receives material from interstellar space, dust, gas, and occasional larger objects like 3i Atlas. This constant exchange means that star systems are not isolated islands, but are connected by streams of matter flowing through the galaxy. The rate of this material exchange has profound implications for our understanding of planetary formation and evolution. If interstellar objects like 3i Atlas are common, then every forming planetary system receives contributions from multiple other star systems. The chemistry of planets might be influenced not just by local conditions, but by the integrated chemistry of the galactic neighborhood. Earth itself might be a composite, built from materials that originated around many different stars, delivered over billions of years by countless objects like 3i Atlas. This cosmic mixing has implications for the search for life beyond Earth. If organic molecules and potentially even microorganisms can travel between star systems, then life might not arise independently on each habitable world. Instead, it might spread through the galaxy like seeds dispersed by the wind, taking root wherever conditions are suitable. This would mean that if we ever find life elsewhere, it might be related to life on Earth, sharing a common ancestor that lived billions of years ago in some unknown star system. The study of material exchange between star systems is still in its infancy. We've only recently developed the ability to detect interstellar objects like 3i Atlas, and we're still learning how to interpret the information they carry. But as our detection capabilities improve, as we discover more interstellar visitors, we'll build up a better picture of how material flows through the galaxy, how star systems influence each other across vast distances, how the galaxy functions as an interconnected system, rather than a collection of isolated parts. Now, as you continue to relax, feeling the gentle rhythm of your breathing, let's turn our attention to one of the most profound ideas in astrobiology, an ancient concept that has been given new life by the discovery of interstellar objects like 3i Atlas. This is the idea of panspermia, the hypothesis that life can spread through space, jumping from world to world, star system to star system, carried by natural processes rather than deliberate space travel. It's an idea that transforms our understanding of life from a local phenomenon, something that arises independently on each suitable world, to a cosmic phenomenon, something that spreads through the galaxy like a slow, patient wave. The word panspermia comes from Greek, meaning seeds everywhere, and it captures the essence of the idea beautifully. Just as plants on Earth spread their seeds through various mechanisms, wind, water, animals, life might spread through space using comets, asteroids, and interstellar objects as vehicles. It's a romantic notion, but it's also one that's increasingly supported by scientific evidence. We know that some organisms can survive in space. We know that rocks can be transferred between planets, and now we know that objects can travel between star systems. All the pieces are in place for panspermia to be possible. The modern version of panspermia, sometimes called lithopanspermia, to emphasize the role of rocks in carrying life, is based on several key observations. First, we know that impacts on planets can eject rocks into space, with enough velocity to escape the planet's gravity. We have meteorites from Mars and the Moon here on Earth, proof that material can be transferred between worlds. Second, we know that some microorganisms can survive the journey through space. Experiments have shown that bacterial spores can survive exposure to the vacuum, cold, and radiation of space for extended periods, especially if they're protected inside rocks. The discovery of interstellar objects like 3i Atlas adds a new dimension to the panspermia hypothesis. If life can survive the relatively short journey between planets in the same solar system, could it also survive the much longer journey between stars? The challenges are certainly greater. The journey takes millions or billions of years instead of thousands. The radiation exposure is more intense, the cold is more profound. But life, as we've learned from studying extremophils on Earth, is remarkably resilient. organisms have been found thriving in conditions that would kill most life forms instantly. In boiling water, in solid ice, in pure acid, in intense radiation fields. Consider the journey that a microorganism would need to survive to travel from one star system to another, aboard an object like 3I Atlas. First, it would need to survive the impact that ejected its host rock from its home planet. This is actually one of the easier challenges. Studies have shown that rocks can be ejected from planets at relatively low shock pressures that many microorganisms could survive, especially if they're deep inside the rock. Then comes the long journey through interstellar space. Here, the main challenges are radiation, cold, and time. Radiation is perhaps the biggest threat to life in space. Cosmic rays and solar radiation can damage DNA and other biological molecules, eventually killing even the hardiest organisms. But if the organisms are deep inside a rock, protected by several meters of material, the radiation dose is greatly reduced. Some calculations suggest that microorganisms could survive inside rocks for millions of years, possibly even billions of years if they're in a state of complete dormancy. The cold of interstellar space, while extreme, might actually help preserve organisms by slowing all chemical reactions, including those that lead to degradation. The question of whether organisms could remain viable for the billions of years needed for interstellar travel is still open. We know that bacterial spores can survive for millions of years on Earth. Viable spores have been recovered from amber and salt deposits that are tens of millions of years old. But billions of years is a different timescale entirely. Over such vast periods, even DNA in complete stasis would slowly degrade from natural radioactivity and quantum mechanical processes. However, if the organisms could occasionally repair themselves, perhaps during brief warming episodes when passing near stars, they might be able to reset their biological clocks and extend their viability. The arrival phase of the journey presents its own challenges. As an object like 3I Atlas enters a new solar system and warms in the light of a new sun, any dormant organisms would need to survive the temperature changes, the sublimation of surrounding ice, and potentially the exposure to a new radiation environment. If they're released from the object as it sheds material, they would need to find their way to a suitable environment, perhaps captured by a planet's atmosphere, or delivered to its surface in dust particles. The conditions on 3 Atlas itself might be more hospitable to life than we might initially think. While the surface is exposed to the harsh environment of space, the interior could be more protected. If 3I Atlas contains radioactive elements, as most solar system objects do, their decay would provide a small but steady source of heat. This could maintain liquid water in the interior, at least for part of the journey. Some scientists have suggested that the interiors of large comets could harbour liquid water for millions of years, potentially providing a refuge where life could survive or even thrive during the interstellar journey. The organic chemistry occurring on and within 3I Atlas could also be relevant to panspermia. Even if no living organisms are present, the complex organic molecules that form through radiation chemistry could serve as food for any organisms that happen to be present, or as raw materials for life to emerge if 3I Atlas delivers these organics to a suitable environment. The constant formation of new organic molecules through radiation chemistry means that 3 Atlas is not just a passive carrier, but an active chemical factory, potentially creating the building blocks of life as it travels through space. The implications of panspermia, if it's real, are profound. It would mean that life on Earth might not have originated on Earth, but could have come from elsewhere, delivered by comets or asteroids or interstellar objects billions of years ago. It would mean that we might be aliens on our own planet, descendants of microorganisms that evolved around another star. It would also mean that life on Earth might have siblings elsewhere in the galaxy, other worlds seeded by the same source, sharing a deep biological connection across the vast distances of space. This idea of cosmic ancestry is both humbling and inspiring. It connects us to the cosmos in a very literal way, making us part of a galactic community of life that transcends individual star systems. If panspermia is real, then the search for life elsewhere in the universe becomes a search for our cosmic relatives, for other branches of the same tree of life that spans the galaxy. Every habitable world might be an experiment in evolution, starting with the same or similar seeds, but developing in unique directions based on local conditions. The discovery of interstellar objects like 3I Atlas gives us new ways to test the panspermia hypothesis. If we could sample the material from 3I Atlas, we could look for organic molecules, for patterns in their chemistry that might indicate biological origin, perhaps even for preserved microorganisms or their remains. While we can't physically sample 3I Atlas with current technology, we can study the material it releases, looking for biosignatures in its spectrum, unusual isotope ratios that might indicate biological processing or other signs that it carries or has carried life. Future missions to interstellar objects could directly test for panspermia. Imagine a spacecraft that could rendezvous with an object like 3I Atlas, collect samples, and return them to Earth for analysis. Or better yet, a spacecraft equipped with a sophisticated biological laboratory that could search for life in situ, avoiding the risk of contamination that comes with sample return. Such missions are beyond our current capabilities but not beyond our imagination, and they represent one of the most exciting frontiers in astrobiology. The rate at which interstellar objects pass through our solar system has important implications for panspermia. If objects like 3I Atlas are common, passing through every few years, then the opportunity for life to spread between star systems is frequent, at least on cosmic timescales. Over billions of years, every star system would have been visited by millions of interstellar objects, each one a potential carrier of life or its building blocks. This would make panspermia not just possible but almost inevitable, a natural consequence of the exchange of material between star systems. The question of whether panspermia has actually occurred, whether life has actually spread between star systems, remains open. We don't yet have definitive evidence one way or the other, but the mere possibility changes how we think about life in the universe. Instead of each habitable world being an isolated experiment in biogenesis, they might all be connected, part of a vast network of life that spans the galaxy. 3I Atlas, whether or not it carries life, is a reminder of these connections, a physical link between our solar system and the rest of the galaxy. As you continue to breathe slowly and deeply, feeling more relaxed with each passing moment, let's reflect on another interstellar visitor that preceded 3I Atlas, one that captured the world's imagination and raised many of the same questions we're exploring tonight. This was Oumuamua, a name that means scout or messenger in Hawaiian, discovered in October 2017 as it was already heading away from the Sun, having made its closest approach unseen by human eyes. Oumuamua was our first confirmed interstellar visitor, the first object we've ever detected that we knew for certain came from another star system. Its discovery was a watershed moment in astronomy, proof that interstellar objects not only exist, but pass through our solar system frequently enough that we can detect them with current technology. Oumuamua opened our eyes to a new class of celestial objects, messengers from other stars that carry information about distant solar systems, and it paved the way for our understanding of objects like 3I Atlas. What made Oumuamua particularly intriguing was its unusual properties. Unlike 3I Atlas, which appears to be more comet-like, Oumuamua showed no signs of outgassing despite passing relatively close to the Sun. It didn't develop a coma or tail, leading astronomers to initially classify it as an asteroid rather than a comet. But then observations revealed something unexpected. Oumuamua was accelerating away from the Sun faster than gravity alone could explain, a phenomenon called non-gravitational acceleration that's usually associated with comets and their outgassing. The shape of Oumuamua was another mystery. Based on its dramatic variations in brightness as it rotated, astronomers concluded that it was highly elongated, perhaps 10 times longer than it was wide. This cigar-like or pancake-like shape is unlike anything we've seen in our own solar system, where most small bodies are roughly potato-shaped. Some scientists suggested that Oumuamua's unusual shape might be the result of tidal forces during a close encounter with its parent star, or perhaps collisions that stripped away material preferentially from certain directions. The colour of Oumuamua provided another piece of the puzzle. It appeared reddish in colour, similar to some objects in the outer solar system, suggesting a surface covered in organic compounds that have been irradiated over long periods. This reddish colour, caused by complex carbon chains called tholins, told us that Oumuamua had been travelling through space for a very long time, long enough for cosmic rays to significantly alter its surface chemistry. Yet despite this evidence of long exposure to space, Oumuamua showed no signs of the ice we might expect in an object from the cold outer regions of a solar system. The non-gravitational acceleration of Oumuamua sparked intense debate in the scientific community. If it wasn't outgassing like a normal comet, what was causing it to accelerate? Various hypotheses were proposed. Perhaps it was outgassing, but with a gas that's harder to detect like molecular hydrogen. Perhaps it was being pushed by radiation pressure, which would require it to be unusually thin and light like a cosmic sail. Some scientists even suggested, somewhat controversially, that Oumuamua's properties were so unusual that we should consider the possibility it was artificial, a piece of alien technology rather than a natural object. While the artificial hypothesis captured public imagination, most scientists favoured natural explanations. One intriguing possibility is that Oumuamua was composed of exotic ices that we don't commonly see in our solar system, perhaps hydrogen ice that would sublimate at very low temperatures and be difficult to detect. Another possibility is that Oumuamua was a fragment of a larger body that was torn apart by tidal forces, giving it its unusual shape and perhaps unusual composition. The truth is, we may never know for certain what Oumuamua was, as it's now too far away to study in detail. The trajectory of Oumuamua told us something about its origin. By tracing its path backward, astronomers tried to determine where it came from, which star system might have been its home, but the results were inconclusive. Oumuamua had been travelling for so long that the gravitational influences of many stars had altered its trajectory, making it impossible to pinpoint a specific origin. It could have come from any of thousands of star systems ejected millions or billions of years ago. The velocity of Oumuamua relative to the Sun was interesting in its own right. It was moving at about 26 kilometers per second relative to our solar system, which is close to the average velocity of stars in our neighbourhood. This suggested that Oumuamua wasn't ejected from its home system at high velocity, but rather drifted away gently, perhaps pushed by radiation pressure or carried away during the dissolution of its parent star's planetary system. This relatively low velocity also meant that Oumuamua had probably been travelling for a very long time, perhaps billions of years. Comparing Oumuamua to 3I Atlas reveals both similarities and differences that help us understand the diversity of interstellar objects. Both are visitors from other star systems. Both are on hyperbolic trajectories that will carry them back to interstellar space. And both have properties that challenge our understanding based on solar system objects. But while Oumuamua appeared inactive and asteroid-like, 3I Atlas shows signs of cometary activity. While Oumuamua was highly elongated, 3I Atlas appears to be more typically shaped. These differences suggest that interstellar objects, like solar system objects, come in a wide variety of types. The discovery of both Oumuamua and 3I Atlas in just a few years suggests that interstellar objects are relatively common. Statistical analyses based on these discoveries indicate that there might be trillions of interstellar objects in our solar system at any given time, most too small or too distant to detect with current technology. This vast population of cosmic wanderers represents an enormous repository of information about other star systems, if only we could access it. The second confirmed interstellar object, 2I Borisov, discovered in 2019, provided yet another data point. Unlike Oumuamua, Borisov looked remarkably like a normal comet from our own solar system, with a clear coma and tail, normal outgassing behaviour, and a composition that seemed familiar. This was both reassuring and puzzling. Reassuring because it suggested that the processes that form comets might be universal, occurring in much the same way around other stars. Puzzling because if Borisov was so normal, why was Oumuamua so weird? The diversity among just these three interstellar objects, Oumuamua, Borisov, and 3I Atlas, hints at the enormous variety that must exist in the full population. Each star system has its own history, its own chemical composition, its own dynamics that influence the objects that form there. The interstellar objects we detect are samples from this vast diversity, each one teaching us something new about how planetary systems form and evolve throughout the galaxy. The detection of these objects also tells us about our improving capabilities. Oumuamua was discovered by pan-stars, Borisov by an amateur astronomer with a homemade telescope, and 3I Atlas by the Atlas system. Each discovery involved different equipment and techniques, showing that we're getting better at finding these objects through multiple approaches. As our detection capabilities continue to improve, with new surveys coming online and existing ones being upgraded, we can expect to find more interstellar objects, perhaps eventually detecting them routinely. The future of interstellar object research is bright. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will survey the entire visible sky every few nights with unprecedented sensitivity. It's expected to discover many more interstellar objects, perhaps dozens per year. With a larger sample, we'll be able to study the population statistics of interstellar objects, understanding their size distribution, their composition range, their orbital characteristics. We'll move from studying individual objects to studying the population as a whole. Some scientists have proposed missions to intercept and study interstellar objects up close. These missions would need to be ready to launch at short notice, as we typically have only a few months or years warning before an interstellar object makes its closest approach to the Sun. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, will wait in space for an interesting target, possibly an interstellar object, then rapidly deploy to study it. Such missions could provide the detailed observations we need to truly understand these cosmic visitors. The possibility of sample return from an interstellar object is even more exciting. Imagine having actual material from another star system in our laboratories, being able to study it with all the sophisticated techniques available on Earth. We could measure isotope ratios with incredible precision, look for presolar grains, search for organic molecules or even signs of life. Such samples would be among the most valuable scientific materials ever collected, providing direct information about conditions in other star systems. The study of Oumuamua has also taught us about the limitations of our current understanding. Despite intensive observations by many of the world's best telescopes, we still don't fully understand what Oumuamua was, or why it behaved the way it did. This humbling experience reminds us that the universe still holds many mysteries, that there are phenomena we haven't yet encountered or imagined. Each new interstellar object we discover might challenge our assumptions and force us to expand our theories. The cultural impact of Oumuamua extended far beyond the scientific community. It captured public imagination in a way that few astronomical discoveries do, while inspiring countless articles, documentaries, and even science fiction stories. The idea that we had been visited by an object from another star system, possibly even an artificial object, resonated with our deep curiosity about our place in the universe and the possibility of life elsewhere. Oumuamua became a cultural phenomenon, a symbol of our cosmic connections and the mysteries that still await discovery. The comparison between Oumuamua and 3I Atlas brings us naturally to the unspoken question that hovers at the edge of our consciousness whenever we contemplate these interstellar visitors. What if 3I Atlas carries something more than just ice and dust? Not in the sense of deliberate cargo or intentional messages, but something more subtle, more profound, information encoded in its very structure, in the arrangement of its atoms, in the patterns of its chemistry. This isn't about alien artifacts or technological devices. but about the possibility that 3i Atlas might carry messages we haven't yet learned to read, stories written in a language we're only beginning to understand, the language of cosmic chemistry and physics. Consider for a moment the nature of information itself. We tend to think of information as something that requires intention. Words written on a page, data stored in a computer, DNA encoding the instructions for life. But information can exist without intention, without consciousness, without any deliberate act of communication. The rings of a tree carry information about past climates, though the tree never intended to create a historical record. The layers of rock in a cliff face tell the story of ancient seas and volcanic eruptions, though no one wrote that story deliberately. In the same way, 3i Atlas carries information about its origin, its journey, its experiences, encoded in every aspect of its being. The isotopic ratios in 3i Atlas are like fingerprints, unique identifiers that tell us about the nuclear processes that created its atoms. Every star has its own nuclear signature, its own way of fusing hydrogen into helium and heavier elements, influenced by its mass, its age, its composition, its history. The atoms in 3i Atlas were forged in a stellar furnace different from our Sun, and they carry the memory of that forging in their nuclear structure. If we could read these isotopic signatures with perfect precision, we could learn about the star that gave birth to 3i Atlas, about the conditions in its nuclear core, about the stellar processes that created the elements we see. But the information carried by 3i Atlas goes deeper than just isotope ratios. The molecular structure of its ices tells us about the temperature and pressure conditions under which they formed. The crystal structure of water ice, for instance, changes depending on how quickly it freezes and under what conditions. There are at least 17 different forms of water ice, each stable under different conditions, and the particular forms present in 3i Atlas would tell us about its thermal history. Did it form slowly in the cold outer reaches of its parent system, or quickly in a more chaotic environment? Has it been heated and refrozen during its journey? The ice remembers, even if we don't yet know how to fully read its memory. The organic molecules potentially present in 3i Atlas carry their own form of information. The specific types of organic compounds, their chirality, whether they're left-handed or right-handed molecules, their complexity and arrangement, all of these encode information about the chemical processes that created them. On Earth, biological processes tend to produce organic molecules with specific chiralities, while non-biological processes usually produce equal mixtures of left and right-handed molecules. If 3i Atlas contains organic molecules with a preferred chirality, it might hint at biological processes in its parent system, though we would need to be careful not to overinterpret such evidence. The surface features of 3i Atlas, could we see them in detail, would tell stories of impacts, erosion, and space weathering accumulated over billions of years. Every crater would be a timestamp, marking an encounter with another object. The depth of space weathering would indicate how long 3i Atlas has been exposed to cosmic rays. Patterns of erosion might reveal past episodes of heating and outgassing. The surface is like a book written in the language of physics, each feature a word or sentence in a story that spans cosmic time. Even the trajectory of 3i Atlas carries information. Its velocity relative to our Sun, the angle at which it entered our solar system, the precise shape of its hyperbolic orbit. All of these encode information about where it's been and where it's going. While we can't trace its path back to a specific star due to the gravitational perturbations it has experienced, the general characteristics of its orbit tell us about the dynamics of our galactic neighborhood, about the typical velocities and directions of objects in interstellar space. The rotation of 3i Atlas is another carrier of information. The rate at which it spins, the orientation of its rotation axis, whether it tumbles chaotically or rotates smoothly, all of these tell us about its history. Collisions tend to set objects spinning or change their rotation. Outgassing can speed up or slow down rotation through the rocket effect of escaping gases. Tidal forces during close encounters with massive objects can alter rotation. By studying how 3i Atlas rotates, we can infer something about the events it has experienced during its long journey. The question of whether 3i Atlas might carry information in a more organized, perhaps even intentional way, is one that we must at least consider, even if the probability seems vanishingly small. We know that our own spacecraft, like the Voyager probes, carry messages intended for any intelligence that might find them. Could another civilization have done something similar? Not necessarily with 3i Atlas specifically, but with objects like it. The idea seems fantastical, but in the spirit of scientific inquiry, we must remain open to all possibilities while demanding extraordinary evidence for extraordinary claims. If an advanced civilization wanted to send information across interstellar distances, embedding it in natural-looking objects might be an effective strategy. Such objects would be more likely to survive the journey than obvious artifacts, which might be destroyed by collisions or radiation. The information could be encoded in subtle ways, in specific isotope ratios that don't occur naturally, in artificial molecules that serve as markers, in microscopic structures that preserve data. We wouldn't necessarily recognize such information unless we looked for it specifically, with techniques we might not yet have developed. But even without any intentional messages, 3i Atlas might carry information about life in its parent system, if life exists there. The presence of certain gases in its ice could indicate biological processes. Methane and oxygen together, for instance, would be suggestive of life, as these gases react with each other and wouldn't coexist for long without being replenished. Complex organic molecules with specific patterns might indicate biological origin. Microscopic structures preserved in the ice could be fossils of microorganisms. While we have no evidence that 3i Atlas carries any such biosignatures, the possibility reminds us to look carefully and keep an open mind. The way 3i Atlas responds to heating as it passes through our solar system is itself a form of information transmission. As different ices sublimate at different temperatures, they're released in a sequence that tells us about the object's composition. It's like 3i Atlas is slowly revealing its secrets as it warms, unpacking information that has been frozen in place for eons. The gases released, the dust particles ejected, the changes in brightness and color, all of these are messages from 3i Atlas about its nature and history. The interaction between 3i Atlas and our solar system creates new information that didn't exist before. The way our sun's radiation affects 3i Atlas, the way Jupiter's gravity slightly perturbs its orbit, the way the solar wind shapes its tail if it develops one. All of these interactions create new patterns, new structures, new information. In a sense, our solar system is writing its own signature on 3i Atlas, adding a new chapter to its story that it will carry with it back into interstellar space. This bidirectional exchange of information is profound. 3i Atlas brings information to us from another star system, and we send information back with it to interstellar space. If 3i Atlas eventually encounters another star system, it will carry traces of its encounter with our sun, our planets, our solar wind. Any civilization that studies it in the future might be able to detect these traces, to know that 3i Atlas passed through a system with a G-type star and multiple planets. We're participating in a cosmic conversation, even if we're not conscious of all the messages being exchanged. The electromagnetic radiation that 3i Atlas reflects and emits is another form of information transmission. The spectrum of this radiation, encoded with information about 3i Atlas's composition and state, spreads out through space at the speed of light. Long after 3i Atlas has left our solar system, the light it reflected while it was here will continue traveling through space, carrying information about this interstellar visitor to anyone with instruments sensitive enough to detect it. In a very real sense, 3i Atlas is broadcasting information about itself and about its encounter with our solar system to the entire universe. The gravitational influence of 3i Atlas, tiny though it is, also carries information. As it passes through our solar system, it exerts minute gravitational forces on everything around it, planets, asteroids, spacecraft. These forces are far too small to measure with current technology, but they exist nonetheless, and they carry information about 3I Atlas's mass and trajectory. Gravitational waves, ripples in space-time itself, are produced whenever masses accelerate, and 3I Atlas's passage through our solar system generates these waves, though they're far too weak for us to detect. Nevertheless, the information is there, propagating through space at the speed of light, a gravitational whisper about an interstellar visitor. The possibility that 3I Atlas might carry quantum information is even more speculative but fascinating to consider. At the quantum level, particles can be entangled, sharing information instantaneously regardless of distance. If atoms in 3I Atlas are quantum entangled with atoms in its parent system, or in other fragments ejected from the same source, then measuring properties of 3I Atlas could, in principle, affect the quantum state of particles light years away. While this seems like science fiction, quantum entanglement is real, and we're only beginning to understand its implications for information transmission across cosmic distances. The chemical gradients within 3I Atlas encode information about its formation environment. Just as tree rings vary in width depending on annual weather conditions, the chemical composition of 3I Atlas might vary with depth, recording changes in its formation environment over time. If 3I Atlas formed by accretion in a protoplanetary disk, its inner layers might have different compositions than its outer layers, reflecting the evolution of the disk as the parent star aged and the disk chemistry changed. Reading these chemical gradients would be like reading a history book written in molecules. The porosity and density structure of 3I Atlas carries information about the physical processes that shaped it. Is it a solid chunk of ice and rock, or a loosely bound rubble pile? Are there voids inside it, perhaps cavities where volatile ices have sublimated away during previous warming episodes? The answers to these questions tell us about how 3I Atlas formed, whether it condensed gently from the protoplanetary disk or was assembled violently through collisions, and about what it has experienced since formation. Magnetic fields, if present in 3I Atlas, would carry particularly interesting information. Some meteorites contain magnetic minerals that preserve records of ancient magnetic fields from the early solar system. If 3I Atlas contains similar magnetic record, they would tell us about the magnetic environment in its parent system billions of years ago. Since magnetic fields are thought to play important roles in star and planet formation, this information could provide unique insights into how 3I Atlas's parent system evolved. The rate at which different isotopes in 3I Atlas decay radioactively serves as a collection of cosmic clocks, each one ticking at its own rate, measuring different timescales. Short-lived isotopes tell us about recent events, perhaps cosmic ray exposure during the interstellar journey. Long-lived isotopes tell us about the age of the material, when it first condensed from the stellar nebula. By reading these multiple clocks, we can construct a timeline of 3I Atlas's history, from formation to the present day. As you continue to relax, feeling the gentle pull of sleep beginning to embrace you, consider how the information carried by 3I Atlas connects to larger questions about information in the universe. Is information fundamental to reality, as some physicists suggest? Is the universe itself a kind of information processing system, with objects like 3I Atlas serving as packets of data flowing between the nodes of stellar systems? These are deep questions that touch on the nature of reality itself, questions that the study of objects like 3I Atlas might help us begin to answer. The preservation of information in 3I Atlas over billions of years is remarkable when you think about it. On Earth, information tends to degrade over time. Books decay, hard drives fail, even DNA mutates. But in the cold vacuum of interstellar space, information can be preserved almost indefinitely. 3I Atlas is like a cosmic time capsule, carrying information from the deep past into the present, and from here into the deep future. It's a bridge across time as well as space, connecting different eras of cosmic history. the question of what information we might be missing, what messages 3i Atlas might carry that we don't know how to read, is both frustrating and exciting. Every generation of scientists has discovered new ways to extract information from celestial objects, new techniques that reveal previously hidden aspects of their nature. Future generations will undoubtedly discover things about 3i Atlas that we can't even imagine, reading information that's there but invisible to us with our current understanding and technology. As we move into our final contemplation of the night, let's embrace the wonder that 3i Atlas represents, the gift of mystery and possibility that it brings to our lives. In a universe that can sometimes seem cold and mechanical, governed by implacable laws of physics, objects like 3i Atlas remind us that there's still magic in the cosmos, still mysteries to solve, still wonders to discover. The true gift of 3i Atlas is not any specific piece of information it might carry, but the sense of wonder it inspires, the questions it raises, the way it expands our imagination and connects us to the vast, beautiful, mysterious universe we inhabit. Think about what it means that we live in a time when we can detect and study objects like 3i Atlas. For all of human history until just a few years ago, interstellar objects passed through our solar system unseen, unknown, their secrets hidden from us. Our ancestors looked up at the night sky and wondered what was out there, but they had no idea that messengers from other stars were passing by, just too faint to see with the naked eye. We are the first generation of humans to know for certain that our solar system is visited by objects from other stars, the first to be able to study these cosmic wanderers and learn from them. This is a profound privilege and responsibility. We're witnessing events that happen on timescales far longer than human history, seeing objects that have been travelling since before our planet formed. We're the universe's way of understanding itself, conscious beings capable of detecting and interpreting these cosmic messages. In studying 3i Atlas, we're not just doing science, we're participating in the universe's self-discovery, helping the cosmos learn about itself through our observations and insights. The questions that 3i Atlas raises are as valuable as any answers it might provide. What else is out there that we haven't discovered yet? How common are interstellar objects? Do they really carry organic molecules, or even life between star systems? How did 3i Atlas form, and what can it tell us about its parent system? These questions drive us to develop new technologies, new theories, new ways of understanding the universe. They inspire young people to become scientists, engineers, explorers of the cosmic frontier. They remind us that there's still so much to learn, so much to discover. The international collaboration involved in studying 3i Atlas is itself a beautiful thing. Astronomers from different countries speaking different languages, coming from different cultures, all working together to understand this visitor from another star. Political boundaries become irrelevant when we're studying something that comes from beyond all terrestrial concerns. 3i Atlas reminds us that we're all citizens of Earth, all part of the same species trying to understand our place in the universe. It's a unifying force, bringing humanity together in shared wonder and curiosity. The technological achievements that allow us to study 3i Atlas are remarkable testimonies to human ingenuity. The telescopes that detected it, with their precisely figured mirrors and sensitive electronic detectors, represent centuries of accumulated knowledge and engineering skill. The computers that process the data, performing billions of calculations per second, are marvels of human design. The global communication networks that allow astronomers to share observations instantly are triumphs of cooperation and technology. All of this, built by curious apes on a small planet, allows us to study a visitor from another star. But beyond the technology and the science, there's something deeply emotional about our encounter with 3i Atlas. It touches something primal in us, the same wonder our ancestors felt when they looked up at the stars and told stories about the patterns they saw. 3i Atlas is a character in the newest chapter of humanity's cosmic story, a mysterious stranger passing through our neighborhood, leaving us with more questions than answers. It's a reminder that the universe is full of surprises, that no matter how much we learn, there will always be mysteries to captivate us. The fleeting nature of our encounter with 3i Atlas adds poignancy to our observations. We have such a brief time to study it before it disappears back into the darkness, never to return. Every observation is precious, every piece of data a gift that we might not get again. This temporal pressure reminds us to value the present moment, to make the most of the opportunities we have, because they won't last forever. 3i Atlas is teaching us about cosmic impermanence, about the transient nature of all encounters, all experiences. Yet even as 3i Atlas leaves us, it opens doors to future discoveries. Now that we know interstellar objects can be detected, we'll look for more of them. We'll build better instruments, develop better techniques, prepare for the next visitor. Each interstellar object we discover will add to our understanding, building up a picture of the galaxy that's richer and more complex than we imagined. 3i Atlas is not an ending but a beginning, the first notes in a symphony of discovery that will play out over generations. The possibility that we might one day send a mission to intercept an object like 3i Atlas fills us with excitement. Imagine a spacecraft racing to catch up with an interstellar visitor, matching its velocity, studying it up close, perhaps even collecting samples to bring back to Earth. Such a mission would be one of the greatest adventures in human history, a journey to touch a piece of another star system. The samples returned would be treasured beyond measure, studied for generations, revealing secrets we can't even imagine. But even if we never physically reach 3i Atlas or its successors, the mere fact that we can detect and study them from afar is miraculous. We're using the light itself as our probe, reading information encoded in electromagnetic radiation that has bounced off 3i Atlas and travelled millions of miles to reach our telescopes. We're conducting remote sensing at its most extreme, studying an object we'll never touch, learning about places we'll never visit. It's a kind of magic, turning light into knowledge, photons into understanding. The legacy of 3i Atlas will extend far beyond its brief passage through our solar system. The scientific papers written about it will be read by students decades from now. The questions it raises will inspire research programs that continue for generations. The sense of wonder it creates will motivate young people to pursue careers in science and exploration. 3i Atlas is planting seeds that will bloom long after it has disappeared into the darkness. Intellectual and emotional seeds that will grow into new discoveries, new understanding, new wonder. Consider how our perception of 3i Atlas might change over time. Right now, with our current understanding, we see it one way. But as our knowledge grows, as we develop new theories and new ways of understanding the universe, we might reinterpret the data we're collecting today. Future scientists might look back at our observations of 3i Atlas and see things we missed, understand things we couldn't grasp. 3i Atlas is not just teaching us about the universe as we understand it now, but challenging us to expand our understanding, to grow intellectually and scientifically. The philosophical implications of 3i Atlas are as profound as the scientific ones. It forces us to confront our cosmic loneliness and our cosmic connections simultaneously. We're alone in our solar system, the only known life, the only consciousness we're aware of. Yet we're connected to the rest of the galaxy through objects like 3i Atlas, through the exchange of material and information across interstellar distances. We're isolated but not separate, alone but not disconnected. 3i Atlas embodies this paradox, this tension between solitude and connection that defines our place in the universe. The possibility that 3i Atlas might carry evidence of life elsewhere, even if that possibility is remote, keeps us humble about our place in the cosmos. We don't know if we're alone in the universe, if life is common or rare, if intelligence is unique to Earth or widespread throughout the galaxy. 3i Atlas might carry clues to these profound questions, or it might be completely sterile, just ice and rock with no connection to life at all. Either way, it reminds us that the question of life in the universe remains open, one of the great mysteries that drives our exploration and wonder. As you drift closer to sleep, feeling your consciousness beginning to blur at the edges, let the image of 3i Atlas float through your mind. See it as it really is. A small dark object, perhaps a few miles across, tumbling slowly through the vastness of space. It's been travelling for so long that human history is just a blink of an eye in comparison. It's seen stars born and die, watched galaxies rotate, passed through regions of space we can only imagine, and now, for just a brief moment in its immense journey, it's passing through our neighbourhood, close enough for us to see, to study, to wonder about. 3i Atlas doesn't know we're watching it. It has no consciousness, no awareness, no purpose in the human sense. It's simply following the laws of physics, tracing its trajectory through space with mathematical precision. Yet in its unconscious journey, it's teaching us profound lessons about the universe and our place in it. It's showing us that star systems are not isolated islands, but are connected by streams of matter flowing through interstellar space. It's demonstrating that the galaxy is more dynamic and interconnected than we imagined. It's proving that the cosmos still holds surprises, still has secrets to reveal. The atoms that make up 3i Atlas have been on an incredible journey. Born in the nuclear furnace of a star, expelled into space in stellar winds or a supernova explosion, condensed into dust grains in a cooling nebula, accreted into a larger body in a protoplanetary disk, ejected into interstellar space through some cosmic accident, and now passing through our solar system, where conscious beings can observe and study them. It's a journey that spans billions of years and thousands of light years, a cosmic odyssey that connects the birth and death of stars to this moment, right now, as we contemplate these atoms and their story. In a very real sense, we're made of the same stuff as 3i Atlas. The atoms in our bodies were also forged in stars, also travelled through space, also went through cosmic processing before becoming part of Earth and eventually part of us. We're not separate from the cosmos, but part of it, made of star stuff, as Carl Sagan famously said. 3i Atlas is our cosmic cousin, made of similar materials but with a different history, a different journey. In studying it, we're studying a different branch of our cosmic family tree. The questions that 3i Atlas leaves us with are gifts in themselves. What if it does carry organic molecules from another star system? What if those molecules include amino acids or other prebiotic compounds? What if the isotope ratios tell us about stellar processes we haven't seen in our own galaxy? What if its trajectory helps us understand the dynamics of our galactic neighbourhood better? What if future observations reveal something completely unexpected? Something that changes our understanding of planetary formation or stellar evolution, or the prevalence of water in the galaxy? These what-ifs are not just idle speculation, but the seeds of future discovery, the starting points for research that could transform our understanding of the universe. The beauty of not knowing everything about 3i Atlas is that it keeps the universe mysterious and exciting. If we knew everything, if we had all the answers, the cosmos would lose some of its magic. But as long as objects like 3i Atlas keep surprising us, keep raising new questions, keep challenging our assumptions, the universe remains a place of wonder and discovery. Every unanswered question is an invitation to learn more, to look deeper, to expand our understanding. 3i Atlas is reminding us that we're still at the beginning of our cosmic journey, still children learning to read the vast book of the universe. As sleep begins to embrace you more fully, let your mind rest in the peaceful knowledge that while you sleep, 3i Atlas continues its journey. It's moving through space right now, this very moment, carrying its ancient secrets through the darkness. Tomorrow it will be a little farther from the sun, a little harder to see, but still there, still real, still carrying its cargo of cosmic information. And somewhere else in the galaxy, other interstellar objects are beginning their own journeys, perhaps someday to visit our solar system and teach us new lessons about the cosmos. The universe is vast and full of wonders, and we've only just begun to explore it. Objects like 3i Atlas are ambassadors from that vastness, bringing us tangible connections to other stars, other worlds, other possibilities. They remind us that Earth is not separate from the cosmos, but deeply embedded in it, part of a vast web of connections that spans the galaxy. We're not alone in the universe, even if we're the only intelligence we know of, because we're surrounded by these cosmic messengers, these carriers of information from distant places and ancient times. Let the thought of 3i Atlas carry you into peaceful sleep. You're part of a universe that's far grander and more mysterious than our ancestors could have imagined. You live in a time when we can detect visitors from other stars, when we can study objects that have travelled for billions of years to reach us. You're witnessing cosmic events that happen on timescales that dwarf human history. And in your consciousness, in your ability to wonder about these things, you represent the universe's ability to know itself, to be amazed by itself, to ask questions about itself. 3. Atlas will continue its journey long after we're gone, carrying with it whatever secrets it holds, plus new information about its encounter with our solar system. Perhaps millions of years from now, it will pass through another star system, where other conscious beings will detect it and wonder about its origin, just as we're wondering now. They might detect traces of its passage through our solar system, know that it once visited a star with planets, perhaps even deduce something about Earth itself. In this way, 3 Atlas connects not just different places but different times, carrying messages across both space and time in its silent, patient way. The night sky above you, if you could see it now, contains countless stars, and around many of those stars, objects like 3i Atlas are forming, or travelling, or being ejected into interstellar space. The galaxy is full of these cosmic wanderers, each one with its own story, its own journey, its own secrets. Most will never see, never know about, but a few, like 3i Atlas, will pass close enough for us to detect, to study, to wonder about. Each one is a gift, a cosmic surprise, a reminder that the universe is far stranger and more wonderful than we imagine. As you drift into sleep, feeling safe and peaceful in your bed, on this small planet orbiting an ordinary star in a vast galaxy, remember that you're part of something magnificent. You're made of atoms that have travelled across the cosmos. You're conscious matter capable of contemplating its own existence. You're a way for the universe to know and appreciate itself. 3i Atlas, in its silent journey through our solar system, has reminded you of these truths, has connected you to the cosmos in a profound way. Sleep now and dream perhaps of cosmic voyages, of interstellar objects carrying secrets between the stars, of a galaxy where matter and information flow in vast, slow rivers between stellar systems. Dream of a universe where life might spread from star to star on natural vessels like 3i Atlas, where organic molecules formed around distant stars might seed new worlds with the building blocks of life. Dream of future discoveries, future wonders, future mysteries that await our species as we continue to explore and understand the cosmos. The story of 3i Atlas is far from over. As you sleep, astronomers around the world continue to observe it, to gather data, to refine their understanding. New discoveries about its nature might be made tonight, tomorrow, next week. Scientific papers are being written, theories are being developed, missions are being planned. The brief passage of 3i Atlas through our solar system will ripple through human culture and science for years to come, inspiring new questions, new research, new wonder. And somewhere out there in the vast darkness between stars, other objects like 3i Atlas are travelling on their own cosmic journeys. Some are ancient, older than our solar system. Some are young, recently ejected from their parent systems. Some might carry water, organic molecules, perhaps even the seeds of life. Each one is a message in a bottle, cast into the cosmic ocean, carrying information across the galaxy. Most will never be detected, never be known. But a few, a precious few, will pass close enough to conscious beings who can observe them, study them, wonder about them. You're one of those conscious beings, blessed to live in a time when we can detect these cosmic messengers, privileged to contemplate their meaning and significance. As you sleep, you're part of the great human adventure of understanding the universe, part of the generations of humans who have looked up at the stars and wondered. 3 Atlas has added a new chapter to that ancient story, a chapter about connections across interstellar space, about the exchange of matter and information between star systems, about the possibility that we're part of a vast cosmic community we're only beginning to discover. Rest now in the peace of cosmic perspective. Your worries and concerns, whatever they might be, are real and valid, but they exist within a universe of such vastness and wonder that there's always room for hope, always space for amazement, always new mysteries to discover. 3 Atlas reminds us that the universe is not a cold, empty void, but a place of constant activity, constant exchange, constant surprise. Even in the vast darkness between stars, objects are traveling, carrying their secrets, connecting distant places in ways we're only beginning to understand. The gentle darkness that surrounds you as you sleep is the same darkness through which 3I Atlas travels, the same darkness that fills most of the universe. But it's not an empty darkness. It's full of potential, full of hidden wonders, full of objects and phenomena we haven't yet discovered. Every night when you sleep, you're surrounded by the same cosmos that created 3I Atlas, that sent it on its journey, that brought it briefly into our awareness. You're never truly alone because you're always part of this vast, interconnected, wonderful universe. Let your final thoughts before sleep be of gratitude. Gratitude that we live in a universe where objects like 3I Atlas exist, where interstellar visitors bring us messages from other stars, where the cosmos is generous enough to share its secrets with those curious enough to look. Be grateful for the scientists who detected 3I Atlas, who study it, who help us understand its significance. Be grateful for the technology that makes these discoveries possible. Be grateful for your own consciousness, your ability to contemplate these cosmic wonders, to feel awe and curiosity about the universe. And as you finally surrender to sleep, know that the universe continues its patient work while you rest. Stars are forming and dying, planets are orbiting, and objects like 3I Atlas are traveling through the darkness, carrying their secrets from star to star. Tomorrow the universe will still be there, still full of wonders, still ready to surprise and amaze us. 3I Atlas will be a little farther away, continuing its eternal journey, but its visit has left us richer in knowledge and wonder. It has reminded us of our cosmic connections, our place in the grand story of the universe, our privilege of being conscious beings in a cosmos full of mystery and beauty. Sleep peacefully now, cradled by the same gravity that guides 3I Atlas through space, warmed by the same stellar processes that created its atoms, blessed with the same cosmic heritage that connects all matter in the universe. You are part of the cosmos, and the cosmos is part of you. 3 Atlas has reminded you of this fundamental truth, this beautiful reality that underlies all existence. In studying this interstellar visitor, we're really studying ourselves, our origins, our connections to the vast universe that is our home. The journey of 3I Atlas continues, as does your own journey through life and through the cosmos. Both are temporary, both are precious, both are part of the greater story of the universe understanding itself. As you sleep and dream, you're processing the wonder of what you've learned, integrating it into your understanding of the world, preparing to wake tomorrow with a renewed sense of awe about the universe you inhabit. 3I Atlas has given you this gift, this reminder of cosmic wonder, and it asks nothing in return except that you appreciate the mystery and beauty of existence. Good night, fellow traveller through the cosmos. May your dreams be filled with the quiet wonder of interstellar space, the patient journey of cosmic messengers and the beautiful mystery of a universe that still has so many secrets to share. While you sleep, Three-Eye Atlas continues its journey, a silent ambassador from another star, a reminder that we're all part of something vast and wonderful, something that transcends our daily concerns and connects us to the infinite cosmos beyond.